Excuse me. So, this will not be an introductory course to Goldbach's conjecture. It's easy to understand, but hard to prove. But let's not waste any more time and just get right to the proof, or rather, what I think the proof might be. We're going to use a strategy of mathematical logic called proof by contradiction, where we say,
let's suppose it's true.
In this case, George, let's suppose it's false. Let's suppose that the prime numbers simply stop at a given n. I picked two n's, 10,000 and 1 million. So let's start with 10,000. This means if you're calculating the total number of Goldbach partitions for, say, a number like 10,010, 3 plus 10,007 would not be allowed, but 37 plus 9,973 would. So as you approach 10,000, the total number of partitions goes up, and after 10,000, it starts to go down. And finally, we get to the last prime before 20,000, and the Goldbach partitions simply stop. So if our n is 10,000, the Goldbach partitions stop at 2n. Now let's take a look at 1 million. So if the primes stop at 1 million, if you're counting the Goldbach partitions for, say, 1,050,000, 1,008,239 plus 41,761 would not be allowed, but 999,979 plus 50,021 would. So the same thing happens as you approach 1 million. The total number of Goldbach partitions goes up, and then after 1 million they go down, and eventually, when we get to the last prime before 2 million, they stop. For simplicity's sake, I've just been saying 2n. So for our hypothetical scenario where Goldbach's strong conjecture is false, there's a gap of size n in the primes. But what on earth from the real world, in which prime numbers are plentiful, can we compare this to? Well, we just get out our musty, dusty old history book here on page 11, and we have Hadamard and de la Vallée-Poussin's prime number theorem from 1896, a direct consequence of which the number of primes below n is about n over the natural logarithm of n, at least for large n. Therefore, the average gap between those primes would be n over the natural logarithm of n, or just the natural logarithm of n. And the natural logarithm of 10,000 is 9.210344, and the natural logarithm of a million is 13.815511. So, for n greater than 4, the natural log of n is less than n. Therefore, the strong conjecture is true. Well, that's all well and good, but how about that pesky weak conjecture? Well, the weak conjecture states that even and odd integers greater than 5 can be written as the sum of 3 prime numbers instead of 2. This has to be done in 2 parts, one for even numbers and one for odd numbers. We'll do the even numbers first. I'm reading from the script. We'll do even numbers first because under the weak conjecture they behave like the strong conjecture because one of the 3 prime numbers has to be a 2. So let's say that we have our magical formulas for the strong conjecture and for the weak conjecture that will instantly return the total number of Goldbach partitions for any value we plug in. So if n is an even number greater than 5, then the weak function for n will give the same value as the strong function for n minus 2. On to the odd numbers. For odd numbers under the weak conjecture, what happens when the prime numbers stop at a given n? Same thing. We start out, total number partition goes up, and because of the third prime, there are a lot more partitions, incidentally, so we go past n, they drop, eventually reaching 0 at the last prime before 3n. And so, we make the same comparison as above. For an integer n greater than 5, the natural logarithm of n is less than 2n, therefore the weak conjecture is true. Just one more thing before I go. On the Wikipedia page for Goldbach's conjecture, there's under, verified results. There's this huge number here which was singled out because it had a first prime of 9,781. Most Goldbach partitions have a 3 or a 5 as a first prime, but this first prime was unusually high. But how many total Goldbach partitions does this big number have? Well, I actually started to calculate the answer, but then I calculated how much time it would take me to calculate the answer. And with my current equipment, it would take me about 372,000 years to get the answer. But I do also have a laptop, so arguably I could cut that time in half. But I did notice that the ratio of primes to total numbers counted stayed more or less consistent at about 0.0012. So using a simple ratio formula, I can semi-confidently predict that the total number of Goldbach partitions for that first giant number is approximately this second giant number. I'll leave the job to finer minds and faster computers than mine to do the full calculation. And that's the end. Thank you very much for watching.